Welcome, everybody, and welcome to the Morrison Planetarium at the California Academy of Sciences presentation of Tour of the Universe. Now, this Tour of the Universe is something unlike you might have seen in our planetarium. This is going to be completely live, and I am using a program called OpenSpace, a planetarium software that is open source to be able to travel to the edge of our universe and all the way back. Now, my name is Jackie. I am the Planetarium Program Manager, and I'm excited that we are starting our tour of the universe relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. And the ISS, that's the short version of International Space Station, is as far as humans travel into space nowadays. You can fit about 6 astronauts on it at any one time, and it is the largest thing that we have built in space so far. It's about the size of an American football field, or I like to say the Academy of Sciences. So if you've ever been in our building before and walked from one side to the other, you've actually walked the length of the International Space Station. But today, we are actually going to go much farther away from our planet. We are going to see how far our human influence has gone. We are going to see how far humans have physically traveled, how far our spacecrafts have gone, and how far our human communications have gone as well. But for now, the ISS is as far as humans do travel nowadays. Now, it may have looked like it was plummeting towards planet Earth. It wasn't actually. It's only a kind of trick in perspective because we're trying to zoom out from our planet. In fact, we're about 600 kilometers from the surface of the Earth. And as we zoom on out, I can also bring up the path of the International Space Station. And now you might see a line that's kind of orangish color. And this represents its path around our planet. It actually takes the International Space Station about 90 minutes to orbit our planet just once. In fact, you can look at night overhead to see it. All you have to do is go online real quickly to see if it's going to pass over your area or when the next time it will. And then what you're going to be looking for is you're going to be looking for a bright star that's moving very quickly. But let's go ahead and continue our journey because we need to go a lot further in our tour today. And I'm going to go ahead and start to bring up some of the paths of the other objects in our solar system, including going to focus on our closest natural neighbor. And that is the moon. Now, the moon is as far as humans have traveled out into space. In fact, astronauts came out here in the 1960s, and it took them 4 days to get to the moon. Now, even though the moon is our closest natural neighbor, it doesn't mean that it's close in human terms. The moon is around 250,000 miles away from our planet. And as we get farther and farther out from Earth and our solar system, we're going to go distances of millions or billions and sometimes even trillions of miles. And when we get these far distances, and such large distances, it doesn't make sense anymore for us to use miles or kilometers as a measurement of distance. Instead, I am going to use a different yardstick, so to speak, the speed of light, the fastest thing that we know of. Now, if we were actually traveling the speed of light, which is almost 200,000 miles per second, it would take us 1.5 seconds to get to the moon from Earth. So we say that the moon is 1.5 light seconds away from our planet. But let's go ahead and zoom on in a little bit closer to the moon's surface. Now, the moon gives an illusion that it's been hit by more things than us, like asteroids or meteors. But remember, the Earth is a much bigger target, so we actually get our fair share of impacts. The moon has basically zero atmosphere. So that means that there's no weathering, no erosion, and there's no plate tectonics on the moon. So nothing's moving around and reshaping its surface. So everything that we see that impacts the moon just stays there. But let's go ahead and zoom out a little bit further. And I'm going to go ahead and bring up the path of the moon. So you'll start to notice a line that's kind of bluish purple. And we can start to see it around planet Earth. Now, this is the path of the moon around our planet. And it takes about a month for the moon to travel around, just once. Or I like to call it a month because it's not a full month. It's actually 29 and a half days. But let's go ahead and keep on zooming out. And we'll bring up the paths of some of the other objects in our solar system, some of those large objects. And we'll also see the sun. Now, if we could travel the speed of light, it would take us 8.5 light minutes, or 8.5 minutes to get from the sun to Earth. So we call the distance between Earth and the sun 8.5 light minutes away. So we're starting to see some of these distances in like seconds, like minutes. And we can start to see some of the large objects in our solar system, like planets. We can see the path of the rocky planets starting closest to the sun: Mercury, Venus, Earth, and Mars. Further out, we can see Jupiter, Saturn, Uranus, and Neptune. Now, you may notice that there's kind of this sizable gap in between Mars and Jupiter, but this isn't empty space. In fact, we can go ahead and bring up some of the other objects in our solar system, like the asteroid belt. Now, while we're looking at this perspective, I like to talk about a little less known object. It lies within the asteroid belt, and it was called an asteroid at one point. And I'm going to go ahead and bring up its path. Now, it might be a little hard to tell. Let's go zoom on in a little bit closer. So you can see it's kind of in this light blue area. It goes right through that asteroid belt. Any guesses on what this object might be? Well, its name is called Ceres. Now, you may not have heard of Ceres before, and that's completely fine. Many people haven't. But Ceres is what we call a dwarf planet. And I bet you all know of another dwarf planet in our solar system. It's a little bit more well-known, and that is Pluto. And I'm bringing its path up as well in that light blue color. Now, the reason why I like to talk about Ceres and Pluto is because everything that we know about our universe, we put it into categories. We label things. And sometimes that can trip us up a little bit. When we first found Ceres, the one that's in the asteroid belt, we thought it was actually a planet. We didn't know about these other small little objects. But about 300 years ago, we started to get telescopes, and we were noticing that there's actually some other small objects in this area. So we decided that actually it's not a planet. It's called an asteroid, along with these other small objects. So Ceres changed from what was considered a planet to an asteroid. And similarly, this is what happened with Pluto. We thought it was the only thing out here in the outer parts of our solar system. But as our technology got better, our telescopes got better, we started to find more and more things. And by the late 1990s and early 2000s, astronomers found a lot more things. And I'm going to go ahead and bring some of those up right now. These are what we call trans-Neptunian objects. Now, they're mostly small icy objects, but some of them are actually quite large, including one about the size of Pluto. So instead of adding another dozen or so planets for all of us to memorize, astronomers got together of like, okay, maybe we need a new category. So first, let's figure out what is the definition of a planet. And they came up with the idea of, okay, a planet has to have 3 criteria. 1, it needs to orbit a star. Well, Pluto and Ceres do that, so check. 2, it needs to be large enough, massive enough to have its own self-gravity strong enough to pull itself into a round or spherical shape. Both Pluto and Ceres are spherical, so check. And 3, it needs to have cleared its path. It needs a relatively clear orbit. So Ceres goes through the asteroid belt, and Pluto goes through what we call the Kuiper belt. So neither of them fit this criteria, so we created up with a new category called a dwarf planet. Now, I know some people were a little upset when this happened. However, I like to think of this way. Yes, Pluto kind of got a demotion, but Ceres got a promotion. All right. Well, I'm actually going to turn some of these objects on, like the asteroid belt and the Kuiper belt, because they tend to slow down our planetarium software, and we have a lot further to go. But let's go ahead and recap how far we've actually gone so far. So remember that it takes about 1.5 seconds to get to the moon at the speed of light. So it's 1.5 light seconds away from planet Earth. The sun is about 8.5 light minutes away from Earth. And now, if we were to go from one side of Pluto's orbit all the way to the other, it would take us 10 hours traveling the speed of light. And even way out here, we can actually check in on our human influence. We can see how far our spacecrafts have gone. You'll notice a couple of orangish lines that have popped up, and these are the paths of the fastest and farthest spacecrafts. So you'll see the paths of Pioneer 10 and 11 and Voyager 1 and 2 that were sent out in the 1970s. And more recently, we have the path of New Horizons spacecraft, which was sent out to Pluto back in 2015. Now, these are the fastest and farthest spacecrafts, but none of them have traveled as far as light travels in a single day. But let's continue our journey. We still have many, many light years to go. But we are going to start traveling the distances of light years. We'll start to fly past some of the other stars in our galaxy. Now, the closest star to us, well, beyond the sun, is about 4 light years away from us. So that means it would take us 4 years to get there, traveling the speed of light. And even way, way out here, we can actually check in on our human influence. I've brought up a kind of grid, and we'll start to see that it's a sphere with the sun in the center on what we call the radiosphere. And this is how far our first radio and TV signals have gone out into space. Now, the earliest radio signature or signals that were able to escape our planet were sent out in the 1930s. So this is about 90 light years away from us in all directions. Since remember, radio signals are actually traveling the speed of light. Radio is light. And we can actually check in on how many planets we have found outside of our solar system. Every ring is around a star that we have found at least one planet around it. Some of these have multiple planets. And these are what we call exoplanets, planets outside of our solar system. And if you look carefully, you'll actually see that there are some exoplanets inside that radiosphere. So who knows? Maybe there's somebody listening to Nat King Cole. That'd be pretty neat. All right, so we're gonna go ahead and start zooming out. And when we start to zoom this far out, my planetarium software tends to slow down just a little bit. But you'll start to see the large scale structure of our galaxy, the Milky Way. Also, see if you can, how long you can look and find that radiosphere as well. So we live in what we call a spiral bar galaxy. It's pretty flat as a disk, but we have these beautiful spiral arms that's filled of gas and dust and stars. And we are about 2/3 out from the center. And right at the center, you'll see a bright group of stars that are close together in the galaxy. If we could actually see past those stars, the very, very center of our galaxy, you would see, well, actually basically nothing, because there's a supermassive black hole at the center of our galaxy that's about 4 million times the mass of our sun. All right, can you still see that radiosphere? Go ahead and point towards it. You're all correct, because I have no idea where you're pointing. But you can use my arrow real quickly. And it's just at the tip of my arrow. So again, about 2/3 from the center. But let's go ahead and zoom on out, continue our journey. Now, our galaxy has about 4 billion stars, but it's just one galaxy out here in the universe. Every dot we see is not a star, but another galaxy with its own billions and sometimes even trillions of stars. And the colors of these galaxies may make it seem like somebody accidentally spilled some cosmic Skittles in the universe. These aren't the actual colors of the galaxies. This actually shows us the different surveys that mapped the galaxies and the different densities of the galaxies. But if we zoom out further, we can actually start to see the large scale structure of our universe. Now, as we look at the structure of our universe, you might notice some funny things from this map. One, it looks like we are the center of the universe. As far as we are aware, there is no center of the universe. It's actually, again, our perspective. How we are building this map. We are looking out away from us in all directions. So it appears that we are the center. But if we were to go to any one of these other galaxies and we were creating the map, it would appear as if we were the center of the universe. As I mentioned, we're pretty sure there's no center of the universe. It's again just our perspective. And speaking of perspective, you might notice there's some sizable gaps of no galaxies. Well, this is because we live inside a galaxy. And remember when I told you our galaxy is made of gas and dust and stars? Well, the gas and dust actually blocks our view. So we can't see beyond our galaxies in certain directions. So because we haven't mapped them, we're not showing them. So this is all that we have mapped in our universe so far, which is pretty amazing. But let's go ahead and zoom on out just a little bit further. And we're going to start to see some of the earliest objects in our universe, what we call quasars. They are the bright cores of some of the very first galaxies in our universe. And I do mean earliest, because any time that we are looking out into space, we're kind of time traveling in a way. All that distance that we are looking out, that light has to travel. And it takes light a good amount of time to get from where it's shining off of and get into our telescopes. So we're seeing that light of the objects as they were in the past, not how they look today. So for example, when we were looking at the closest stars to us, that kind of 4 light years away from us, that's how those stars looked 4 years ago, not how they look today. So we are now seeing the universe as it was billions of years ago. And because we are looking in the past, there's actually only so far we can look. There's an edge to everything we can see in the universe. And that edge is now this kind of orangish, splotchy picture that we see. This is what we call the cosmic microwave background, or CMB. Now, if you had a radio telescope and you could see in the microwave range of light, you would see this everywhere you looked in the sky. In fact, the first radio astronomers were pretty confused by what they were looking up in the sky. They thought it was actually interference, but they soon realized it was actually something coming from space. And the differences between the really bright areas and the really dark areas is actually showing us temperature variations at the very beginning, few hundred years after the Big Bang. No, few 100,000. So we can actually kind of think of this as the baby picture of our universe. And because this is our baby picture, it means we actually can't go any further. So it is time to send us back home. I promised I wouldn't leave you out in space. Now, if we were actually that far out in space and we were actually flying the speed of light, it would take us 13.7 billion years to get us back home. But thankfully, I have the power of the planetarium software, and we are zooming back home pretty quickly. But one more thing I want to point out as we're zooming back home. All that we have looked at so far, all these stars and galaxies and a cosmic microwave background, that's not everything in our universe. There's dark energy, this mysterious force that's causing space itself to accelerate as it expands. There's dark matter, this mysterious substance that doesn't seem to interact with light at all, but we see evidence of it in between and at the edge of galaxies. And we call all these things dark energy and dark matter. It's because, well, not quite sure what exactly it is. But we do know that it makes up 96% of everything that is out there. So everything that we saw is only 4% of matter in our universe. And that might make us feel a little small, like we're one tiny dot in this homogeneous universe. But I like to think of it this way. Yes, we're one tiny dot, but look at all that we have found, almost entirely by looking through telescopes. So there's a whole lot more for us to discover and a whole lot more for us to learn. And that's what makes it a wonderful time in human history. That we're not just able to explore, categorize, name things, but to be able to map these things. Show the cosmos in 3 dimensions. And we're finally starting to unravel the true nature of the universe. But we're only just starting. The rest, well, that's up to the next generation of scientists back here on planet Earth. So we're heading on home to that third rock from the sun. The only place in all of this that we have found life. And that's pretty incredible to think about. So welcome home, everybody. And thank you for joining us on our tour of the universe. As a reminder, this software is called OpenSpace, Open Planetarium software funded by NASA. If you like this program or any of our other live stream programs from Morrison Planetarium, please let us know. We have a feedback form we would love for you all to fill out. So I want to say thank you again for joining us, everybody, and I hope you have a great rest of your day.